So the program for today, we are almost finished. So the last two classes, I introduced you to these modeling paradigms which are embracing probabilistic description of phenomena. And last week I introduced you to Feynman's text about quantum physics and described the model that he uses in his book to explain what quantum physics is about and how does modeling work there. You remember that it has to do with the kind of harmonic description of phenomena, not geometric. And here there's a table. In this table I've condensed the topics we have covered so far. And we've seen how the notion of space has changed from Descartes to Riemann. And we also discussed how the notion of structure has changed as well. And then we saw the logicists' bottom-up ideas of making structures. Remember from trying to see logic as the root of mathematics. On the other side, you had cybernetics and these kind of top-down ideas, control ideas of making structures. But then, on the other hand, I introduced you to the idea of structurability, which is a kind of abstraction of an idea of even having a structure. And my hypothesis was that this idea of structurability very well corresponds to what we can observe with internet today, which is not predefined and kind of grows from inside out. Then we talked about this idea of global and local and how quantum physics relies on localization and probability theory. And finally, I suggested that the role of computation has also changed. We do not longer consider computers as machines, but we see them as an infrastructure for communication. And my hypothesis is that if we would like to challenge today's computational models in architecture, we should be searching for models that include or are at least compatible with the principles that I have pointed out on this right column. And an interesting thing that I noticed is that these concepts we have on the left, they have something in common in terms of mathematics. And they are very much in tune with a specific mathematical paradigm, which is very dominant still. And we already spoke about this paradigm in the very beginning. I introduced you with the logicists. It's the paradigm of set theory. And what I've also discovered is that computational models in architecture are also following this mathematical conception. And also at the end of the class, you should be able to understand why. But then if this is so, the question is there some kind of mathematical paradigm that is more in tune with these concepts on the right side, in the right column? And this is not a very easy question to answer as an architect. So how did I approach this? So in my search for models that are somehow compatible with the concepts in the right column, I got introduced to two such models. And for 5 years, I was attending a theory colloquium led by the philosopher Vera Billman, who is now a professor in Vienna. And she gave us a lot of references in philosophy, modeling, mathematics, and among a lot of models that she mentioned, I recognized two models that were very much compatible with these concepts on the right side. And one of them came from the theory of language, and another one was created by a quantum physicist. And on my great surprise, I discovered that both of these models were expressed in a very similar mathematical language. And this language was very different from the language of set theory. And both of the models were speaking somehow about communication. And I spent almost a year only concentrating on these two models and realized that the word communication was not simply a coincidence. It was a crucial term in this context. Because for these models that I'm about to show you, modeling is communication. And this is why I've referred to them as models of communication. But before we go there, I would like to recapitulate what set theory is about. Okay. And set theory was introduced by the German mathematician Georg Cantor in his 1874 paper. As the name says, it is a theory that studies sets. And what are they? So Cantor defines sets as collections of objects that are characterized by their membership and in certain case ordering. So if you have an object, existence of any kind of object in set theory has two relations in respect to a set. So object can be a member of a set or not a member of a set. And this binary characteristic of this membership operator, it brings set theory very close to logic. And this paradigm of set theory had, because of that, very enormous influence on modeling, and which is something that I must address. So set theoretical thinking relies on a hidden assumption that all objects we can deal with formally are in fact naturally distinguishable. And this is also reflected in a language. So if I say we have now 40 chairs in this room, this simple statement that I made already contains an assumption. So what is the assumption? So it assumes that I can somehow naturally distinguish and positively identify a chair from the environment, that I can distinguish a chair from other objects that we have around, and that I can distinguish a chair from another chair that looks just like it. And this is a lot of assumptions already embedded in a very simple statement. But because of this simplification on which set theory rests, I can easily count the chairs. I can say, for example, 3 chairs plus 2 chairs equals 5, and so on. But on the other side, what set theory does not allow us to do is to account for things that do not have clear boundaries, or have, for example, temporal nature, such as, for example, photons and electrons. So as soon as we have things which are not naturally distinguishable, which we do not know where they start or stop, just think of clouds or foam, on which change over time in a way that is unpredictable, we cannot use these assumptions. So set theory then becomes a very limiting paradigm. Just to give you an example of prominent set theoretical thinking in architecture, I would say it's, of course, among many others, but this one is very clear. It's Rem Koolhaas's exhibition on the elements of architecture. And Koolhaas asserts there are 15 elements of architecture: the ceiling, the door, the fireplace, the wall, the ramp, the balcony, the toilet, elevator, escalator, corridor, floor, roof, window, stair, and facade. So he says these are the elements. Yeah? And then ironically, he says, let's rethink these elements of architecture. But what this rethinking then asks from us is to affirm his assumption that these are the elements. So this is it. And in this similar way, set theory works. It works only if you buy it. Only if you buy it, then it works. But if you don't buy it, if you say, no, I do not think that these are the elements, what about some other constellation? Well, you don't have a different model. The question is there a kind of modeling paradigm in which you do not have explicitly to say what are the elements? Can you just somehow be more relaxed about this thing and still talk about architecture? And this is my interest in this. And these models that I'm going to introduce you are introducing exactly this. So today's lecture is about 2 models of communication. And as I said, one comes from quantum physics and another comes from language. And my goal here, of course, I'm going to try to, they're abstract and it doesn't matter if you and how far you understand it, but you should get a kind of an intuition. What would modeling be in terms of communication? And then this has 2 aspects. First one is who communicates with whom, or what communicates with what. And the second one is what kind of architectonics makes it possible to communicate. And first, let's examine a kind of traditional common sense view on modeling, something that is kind of that we usually take for granted. And this is the view about problem solving. You will hear that a lot. And the traditional idea of problem solving is that you are on your plane of reference, and on this plane of reference you can recognize your starting point, which is the problem, and you can recognize the end point, which is the solution, which is what you want to have. But the consequence of this linearity that I just depicted here is that sometimes you encounter obstacles on your path of your problem solving. And then these obstacles become the limit of your world. For example, such an obstacle can be infinity, which is very often happens in mathematics, or for example, a void or a singularity with things which happen in physics. But now let's see how a communication model would approach modeling. And the first model I'm going to show you is the model of natural communication created by Elias Zafiris, who is a quantum physicist. And the model of natural communication, it kind of starts from a very different point of view. It starts from the idea that any problem can be accessed on multiple levels, or if you would like, every problem coexists in multiple natures. So if you have an obstacle on the level A, like before, and on this level you have some kind of limit to your world, so somehow kind of obstacle that you cannot surpass, what you can do, you can translate your whole problem situation, so whole domain. You can translate the whole domain to the problem B, and on this other domain, you can imagine this is a kind of different nature of things, this obstacle might not be there. Or there is an obstacle still, but it can be bypassed this time. So what would this allow you in principle is to find a solution for your problem on the level B and then translate the domain back to A and interpret what the solution means in the A. So you translate the whole domain to B, solve it. Now you are on B, you translate it back to A, and you got a solution. And in this way you go around the obstacle. Yeah? And if we have such a model, this model has two elementary requirements which it must satisfy to make this communication possible. And what are these? It needs to have means to encode and means to decode information. So if a model provides means to encode and decode information, we call such a model cryptographic model. So crypto means a cipher. So you might ask, what does a cipher has to do with modeling? So let's see. So first of all, it's important to keep in mind that these two levels that I have shown here, this is not something which is given to us. We do not now see our problem on two levels just like this. But the level B, we for example might know what is our level A, but level B is inaccessible to us. So when we start, we do not know what level B is. Yeah, we know that we need to go to some level B to try to see the thing in a different angle, but we do not know what B is. So B is kind of inaccessible to us. We need to unlock it. Yeah, and to unlock it, we need a cipher, metaphorically speaking. So how is this done? We can think of this encoding and decoding as two bridges. And on the level A, we use the encoding bridge to unlock the level B. So therefore, creating this model which unlocks the level B is a kind of pure creativity act. And this is the crucial thing of modeling. This is how you model. And how do you know if a model is good or not? And according to Zafiris, who is the inventor, this quality of a model is dependent on the quality of these cryptographic bridges. And there's a property which characterizes this quality, and it's called naturality. That's why the model is called.
Can I ask you what a cipher is? Just what the word means.
Someone can try to explain what a cipher is? If you, for example, have a lock.
But not the key. What?
No, it would be a kind of, you can think of it, I'm sorry, it's a little bit difficult to concentrate at the moment, but you need to find a single key which will unlock the domain.
Oh, it's in the.
Yeah. Yeah. So cipher is a principle which allows you to unlock something, so to say. And yeah, so I told you, the quality, how to speak about the quality of a model is with this notion of naturality. So naturality is a property that is concerned with the structural property of a whole domain, and not individual properties of objects. So instead of thinking what are the properties of objects on the level B, we are not concerned about them. We are concerned about the property of the whole level. So this is what we are trying to understand. And if we are able to, in our model, accommodate for the property of the whole level, to describe the whole level, then we have a natural model in the terms of Zaffiris. And we have here an interesting quote by Hermann Weyl, who was one of the very famous mathematicians of ETH Zurich. He says, I quote, "A science can only determine its domain of investigation up to an isomorphic mapping. In particular, it remains quite indifferent to the essence of its object." And this is a very deep quote. End of quote. So what he suggests is that we do not have the access to the essence of things, but we can construct an isomorphic mapping. So what does that mean? So if you ask Zaffiris, who created this model, he would say that in nature, we do not have the direct access to the things that we want to model. For example, we want to model an electron, but the problem is we do not have an access to electron. We cannot measure it, yeah? However, these unknown things that we cannot do, they're always encoded in some kind of structures that we can observe. And Zaffiris calls such structures geometric structures. So this would be what we see on the left side there, yeah? So according to that, Zaffiris describes code as kind of semantic elements of modeling. So you can think of code as mathematically or as, for example, geometrical elements or topological elements, something that are unknown things are encoded into, you know. And so every problem that we can encounter will have, for example, its own geometry or its own topology. But now let's look at the right side. In order to even talk about something which is geometrical or topological, we need to have a conception what geometric means or what topological means in the first place, yeah? So we need to be able to discriminate between something topological and something geometrical. So if you define something as geometrical, you need a key in order to decipher it as geometrical. And this is the idea of a cipher. So you need a key to allow you to decipher something as a geometrical. So if you cannot decipher it, then this thing does not exist for you. You are seeing something and you have no idea what you're looking at. But if you have a cipher, so if you know the principle, then this is geometry, or this is topology. You know, you can distinguish, you can look at things and say, yes, I see this, I see that. This is because of the cipher. You have a cipher which unlocks this thing to you. And Zaffiris, he describes ciphers as algebraic elements of the analysis. Yeah? So we can think of ciphers as kind of models that formalize processes of reasoning and computation by being kind of conceptually isomorphic to what we observe in nature. So by making models, we do not directly decode nature. We do not decode nature. We do not put nature in a shaker and then mix it, you know, in order to get something. What we do, we create models that behave similarly to what we can observe in nature. So they do not really decode the nature. They just behave in a similar way. And by making the isomorphism, by making two things similar, we can then deduce something from that. And from this perspective of codes and ciphers, then the basic idea of this model of natural communication is that you create communication bridges to encode geometrical or topological information into algebraic structures. And as you already know from dealing with problems in algebra, these problems are always solved kind of formally or algebraically. If I write an equation, you know how to solve it. You know what steps to take to solve it, yeah? But now imagine that you have solved your problem in this algebraic domain. So you had it in this domain, and then you transform it into algebraic domain. So your solution is also algebraic, but you have no idea what your solution means. You just know that you solve it, but you do not know what it means. Because you detached geometrical meaning from algebraical, and you have solution in the algebraical, but you do not have solution in the geometrical domain. So what you need to do is construct another key, which goes back and translates the whole domain back so that you can interpret what this solution means. And this is called a decoding bridge. So now you get the semantics back. Now you solved it, and now you know what it means in geometry. So you always this step, go to another level, solve, go back. always making a circle. Now let's introduce you how this key works, how this model works. So the model is illustrated with the so-called Motivic key, and this is the rectangle in the center with these arrows. And he says this is a relational unit. Okay, so what does this key relate? Why is it relational? So it relates 4 things: 2 levels, which stratify our problem, and 2 inverse bridges that encode and decode information. And here we have symbols for them. So we have 2 levels, W and T, and we have S representing encoding and S inverse decoding bridge. You see them there. So the direction of arrows shows us that encoding bridge and decoding bridge, they have they're inverse to each other. So they point in a different direction. And because of this inversion, this is now interesting, we have multiple ways to read this key. And for each reading, we get a kind of different algebraic structure. So if we take W, the one at the top, to be the level of the original problem, then we can say that T, which is on the bottom, is conjugate to W under encoding S1 and decoding S on the -1 or S inverse. And you can describe this as W equals STS. But then what you can also do is reverse the thing. You can say that now we are on the level T, and level W is conjugate to it by means of bridges S -1 and S. So you just need to invert the bridges, and then you point from the level 2 back to the level A. So depending on how you read it, you can use both. Yeah, this means conjugation. You can express one thing in terms of another thing. And then the next important property of this key is the property of extension. So there are 2 types of extensions that you can create, and you can create these. You can use these extensions to create more complex models. We have, for example, extension of the key in depth, as you can see in the middle drawing, and the extension of the key in length. So let's see what they are about. So let's see what is extension in depth. So if we have 2 keys and they share a common level, in this case the common level is T. You see T is in the middle. In such a way that W is conjugate to T and T is conjugate to K. Actually T is conjugate to R, sorry. Then these both keys can be described in their original level, as you can see here and here. So W in terms of T and T in terms of K and R. But if you do a kind of algebraic manipulation, you can also describe W in terms of R. So describe the top one in terms of the bottom one. But this time, the bridges would not be a single bridge. It will be 2 bridges which are composed to each other. So as you can see, composition. S and then K. So if you look at the equation at the very bottom, you will see that this key, new key, which is called key extended in depth, has the same form as the key on the top. It's just, instead of S and S inverse, it has SK and SK inverse. But the middle part is also a single element, yeah? But also, if one key, for example, W, is conjugate to T, like before, and another level A is conjugate to level B below it, under the same bridges, then these 2 keys can be described in terms of the original key, like you have before, so W in terms of S and T, and A in terms of S and B. But now, these 2 things together, you can describe with the so-called product key, which is a product of W and A, and it's described by a key S, by the bridges S and S prime, and in between is the product of levels T and B, as you can see there. So this is not very important. It's just for you to understand that you can use this principle and extend it to create much more complex models. And now let's see how we can use this model to encode, for example, topological problem into an algebraic structure. And this is done on the example of so-called homotopy classes. I showed you this problem before, but now it has a more precise explanation. If you remember, we were talking about covering spaces with Bernard Riemann. So in topology, what homotopy means. What homotopy means, it describes a deformation between two functions so that one can be continuously deformed into another. As you can see on this drawing, you can take one curve, and in any number of steps, you can deform it into another curve. Yeah? Why they can be deformed into each other? Because there is nothing preventing the deformation. And here we have a setup where we can examine homotopic properties of two paths on the surface of the ring. So on the left drawing, you have two paths, blue and green, and they pass through the points A and B. And as if you can see, you can clearly deform the curve AB, I mean the blue curve into the green curve, because there's nothing preventing it. But on the right side, you have blue and red curves, and one of the curves, blue curve, is the same as before, but the red curve now winds around the hole once. The question is, can they be deformed? And we already discussed that they cannot be deformed into each other. Every attempt to morph, for example, blue path into the red necessarily fails, because the path must cross the hole to be deformed, and this cannot happen because hole is the obstacle, is the limit of our world. So simply they live in different worlds, they cannot be deformed. So what does this mean mathematically? Now, how we can now speak about it mathematically, not anymore as a metaphor. So hole here is a structural invariant of a problem. And this invariant property is manifested that if you have a path that winds up around the hole x times, and another path that winds around the hole y times, if x is not equal to y, they cannot be deformed into one another. The only way that they can be deformed into one another is that they wind around the hole the same number of times. The question is, okay, we understand this on the level of topology, on the level of deformation, but how can we encode this into algebraic terms? And this is the simplest example possible how to do this. Remember this animation? You use covering spaces, and what covering space allows you to do is to simply count the number of times that our path winds around the hole, and then you assign a number to a path. So in order to describe the deformation property of any path on this ring, you only need, sorry, I didn't show the animation. The only thing you need is integers. So we encode the geometrical problem of path deformations, or topological, by using the algebraic structure called a ring of integers. And then this result has two benefits. So all this complexity of these winding paths and all of this is reduced to the level of numbers. So, and each integer, so each number, which can be represented with these red spheres on the path, each number has a now geometric meaning. It means how many times a path winds around the hole. So you see, we establish a mapping between geometry or topology and in the numbers theory. So now number has a geometrical meaning, and deformation has meaning in terms of numbers. Yeah. So you have two ways to talk about the same problem. You can describe it topologically, but you can also describe it algebraically with numbers and the properties of numbers. So you can now speak, is this number greater than 1? Is this number the same as 1? You see? But this is the simplest possible case in which this can be done. Yeah? And now, let us consider how modeling with cryptographic keys differs from modeling in set theory, from what we have seen before. So the most important aspect to consider is that how do we think about objects? What are our assumptions about objects? And I want to show you that this is very different. And of course, you only need to understand it conceptually. So here, imagine that you're modeling anything you're modeling. You start from the state of total indistinguishability. And this is called an indiscrete partition. And this state that you encounter when you start modeling, this state is a state of maximum symmetry and no information. And then you employ this encoding bridge that I told you. What this bridge does, it breaks the initial symmetry, and by breaking the initial symmetry, you gain some information. And this information is now in form of spectral differences. What does this mean? This means that it's possible to distinguish something about our unknown object from something else about it. So you're able to distinguish something about it. We do not say what, it doesn't matter. Suddenly, what was completely black box, now you're able to see something in it. Yeah? Think of it as in a very abstract way. So these distinctions that we are now able to see, they are now observables within the partition spectrum. And now to understand what this partition spectrum is about, just consider this colorful circle in the center. This tries to illustrate partition spectrum. And what does it mean? You are able to distinguish some differently colored regions into this disk, no? So it's colorful, but you can see that there are some kind of clusters of colors, yeah? Some are more towards blue, some are more towards red. Yeah, you can see that. So this, for example, let's say that these are our distinctions. So we had something which was completely black to us, and now we do not know what it is, but we know that there is something red, something blue, something whatever. But of course, you do not think in terms of colors only, yeah? We call these things that we can now see, we call them virtual distinctions. And these things that we see, they're not elements, yeah? Like we think in set theory, they are now elements. This is now a house, or this is now a floor, yeah? No. They're not yet actualized. They're not real things. That's why we call them virtual distinctions. So what you can do with them? You can either further refine, so you can take now each of these regions of colors, and then further refine it to find even more clusters within it. Or you can actualize, you can say, yes, this is what I want to describe, how I want to describe my object. And when you say this is the way, how I want to describe my object, you say these virtual things are now real. Now I classify my objects according to the similarity to how do they correspond to these regions, yeah? But if you decide to distinguish more and more and more, like theoretically, if you just want to go further and further and further and further, then you go to this last state on the bottom, which is called a discrete partition. And in this state, you distinguish everything there is about your object. So imagine now you exhausted every possibility of knowing your object. Is this an ideal state? I'm asking you. So this is just a question. So if you are able to distinguish everything about something, is this the ideal state of modeling? What do you think? We are thinking very metaphorically, and conceptually here we are not.
I think you might lose some of the meaning, the relations of the objects. Is what I think when I see this.
Exactly, this is what is happening. You gain a lot of information, but what is the price you pay? What do you lose?
Knowing how they all work together, or
Yes, you lose symmetry. Or context. So you pay price with every modeling decision. If you distinguish most information, you lose symmetry. You lose the context. You do not know what's the context. You have the values, but you don't know what you lose any connection. But in the first place, when you have no information, you have maximal. Everything is full in its potential, but you cannot say anything about it. You understand? It's a very metaphorical distinction here, but also real. So these are two states of kind of extreme states that you can see. And modeling is something in between. Modeling is some kind of decision of how much symmetry and how much information you want to have. And you must know that wherever you want to have more symmetry, you will have less information. So you always pay the price. Yeah? But let's now see how computation looks like in this perspective. And in computer science, when they speak about computation, they usually start with speaking about something called an effective procedure, which was introduced by Turing and Church in 1936. So what this means to have an effective procedure, practically it has to do with a certain, let's say, algorithm or certain thing we do that can be done mechanically. So if someone tells you exact steps what you can do, you will able, by following these steps, to come to a certain result. So this, if you can make such a procedure to follow the steps and get to the result that you know what's going to be, this is an effective procedure. So yeah, I don't want to go into detail. So how computer scientists think about this? They say this effective procedure has a black box, which is some kind of function. So this is kind of these steps. But it has input and output. So you put some input, something happens, some operations, and then you get some output at the end. And then what it means is that you can chain this. So you can chain one procedure into another and another, and you make a huge linear chain, and then you can create a very complex program. You put some inputs and you get some outputs. But you can linearize it. But in this model of natural communication, you do not have a single path. Yeah? The problem with this one linear chain is that it's very specific to a certain problem. You take another problem, it does not work anymore. But what natural communication model tries to do, it says you have at least two chains, and each of them is on their level, so on a different levels of your model, different natures, and they're connected with these bridges, vertical bridges. What these bridges allow you to do is to kind of create a communication between these two computational chains, and in this way, it does not matter. So you need to construct them in a way that both levels are described structurally, so that it does not matter what kind of object you put on a level, it will be able to translate into the other level. But I will talk about that more next time when I can give you an example. Now it's difficult to talk about it just in this very abstract way. And now just a couple of more details about the key. And as I told you, in C++ case, we have two levels, W and T, and they are conjugate to each other under these two bridges, S and S inverse. Yeah? I'm repeating myself a lot because I want to, by repeating, I want you to get this, because I know how difficult it can get. So what the theorist tries to show here is that this relation between these two levels is a special kind of relation, and it's called equivalence relation. So what does this mean? It's a kind of special relation which exists between each possible process which can be stratified on two levels. And it has three properties. It's reflexive, which means that each process is conjugate to itself, which is kind of 1 is equal to 1, which is kind of not something new. This is obvious, but then it has two other properties. It is symmetrical, which means you can describe one level in terms of another. And it is transitive, which means that you can extend it in depth and in length. And now we were discussing having a problem on different levels. But now instead of thinking about one problem being on two levels, now imagine all possible problems on two levels. Theoretical possibility, because this is how it's described mathematically. All possible processes that could be related by different levels. So what is then the role of this key? The role of this key is to stratify all of these possible things, all of these possible classes of processes on different levels in such a way that processes that are equivalent are taken together. So what is equivalent together will end up in the same place, yeah? Belong to the same class. So what happens if you repeat this, what actually happens if you do this to anything is that these things that are similar to each other will be grouped. Therefore, you will have a spectrum of things in which you will recognize certain things from some other things, yeah? So in a simple case scenario, from our black box, we are now possible. It's now possible because of this relation to see something being different from something else. So this is the colorless disk in the center, yeah? And entities that are part of different cells, what is really different between them? So if something is in a blue cell or in a red cell, what is different is that different bridges apply to them. Different bridges apply to blue ones and different bridges apply to red ones. This is why it is possible to distinguish black from blue. So now we obtain this spectrum, and we recognize something which are equivalence classes, and we can now ask what are the elements of this? And again, I need to repeat, these equivalent classes do not contain elements like we can speak about sets. You know, they do not contain chairs on tables or whatever like that. we call them indistinguishable or indistinct types, these things that we can recognize. But there are two things we can do now when we come to this stage. You can either further refine this class, this type, or you can say, yes, I'm satisfied with this. I think I would like to see my object represented in terms of this type. What this does is actualizes the virtual distinction. Yeah? And this can be described with these two basic properties, distinction and differentiation. I don't want to go into detail, but yeah, now I see that I have way too many slides for what I wanted to tell. Maybe this is interesting, I don't know, maybe for architects it is interesting. So if you put things in terms of levels like this relation between these two bridges can be realized in a different code. This is called the code of symmetry. And the simplest code of symmetry is called a group. And this means that these two bridges are inverse to each other. And the simplest way how things can be inverse to each other is, for example, this. If you have 1 and if you have 1/5, would you consider that 1/5 is the inverse of 1? Oh, sorry, 5. 5 and 1/5. Would you say that this is an inverse of 5? By definition. What happens when I multiply 5 and 1/5? What do I get? 1. Yeah, this cancels out, you get 1. So when you multiply two inverses, in the simplest case, you get 1. And what is 1 in mathematics? 1 is so-called identity unit. But now, depending on what these levels are, this identity unit does not need to be so simple. If a cipher of symmetry is group, then you get, they annihilate each other, and the identity becomes fixed identity, 1. That's it. But there are more advanced inverses than that. So for example, if these bridges are not exact inverses to each other, but some kind of different localities on each side, then you have a cipher called groupoid. And finally, something which is very interesting for architects, I would say, these communicational bridges can be conceptual inverses. If they are conceptually inverse, then they are called adjunction. And this is very interesting, because between two levels, you cannot make a very precise mathematical model, which if you would multiply them, you will get some identity, fixed identity. No, this identity will be a fluid identity. It is called homotopic identity. It is kind of oscillating identity. It has a soft boundary. So this is a particularly interesting to architects, because now if we learn how to deal with this, the identity that we establish is not a fixed one. And this is what architects always like, not to have a fixed identity, to always have this oscillating identity which is alive. And I just want to tell you that in this kind of mathematics, we are able to talk about these things, which with ordinary mathematics we could not have. In ordinary mathematics, they annihilate each other, you get a fixed number, that's it. There is no deeper meaning. And here there is. Okay, I will skip this because it's kind of showing the process all over again. And now, let's see what an information is within this natural communication model. And as I told you before, how information is described in set theoretical paradigm is with an example of a set. And as I told you, set assumes things that are completely distinguished. So if you have a set of all possible objects, or any kind of objects that we are dealing with, within this set, we can distinguish a subset. And now, in order to define membership within the subset or of a set, to define whether an element is in a subset or outside of it, we just need this notion of membership. And if the member is within the set, this is a true statement of logic, which is equivalent to 1. And if an element is not a member of a subset, this proposition is false, then we have 0. So in set theory, this classification that something is 1, that something is member of a set, this is a unit of information. This is what we call bit. So a true proposition gives us 1 bit of information. And it is very different what is an information unit in a natural communication model. Because in partition paradigm, you have a spectrum, and then on top of this spectrum, you can see different equivalence classes. So information is being able to distinguish something from something else. Yeah? So if you have two processes, Q and R, information bit would be ordered pair of processes, Q and R, which belong to different equivalence classes. So it's a very different idea. And finally, to describe better a little bit this virtual and actual distinctions. So you have two levels. You have bridges between them. You create a spectrum. You distinguish something from something else, like there, like there. But then, once you decide to go deeper, for example, to deeper explore a certain region, what you first need to do, you need to actualize. You need to confirm your previous state. So you need to confirm what you distinguished previously. And in this way, what used to be a virtual distinction now becomes an actual distinction. When this happens, we do not longer need these bridges which took us there. So we use some bridges to get there, but once we actualize this distinction and go further, we can discard these bridges. So this breaking of the bridges is what causes us to lose symmetry and gain information. So in this way, information and symmetry are two inverse concepts to each other. Yeah, here you can see kind of a table of distinctions between set theoretic paradigm and partition paradigm. I don't want to go into details. You saw it. This is just a summary of everything. But then before that, I told you, you know, I was interested what kind of mathematics would correspond with this kind of modeling on the right. And it turns out that there's a kind of contemporary mathematics within the pure mathematics that we can use to represent this partition paradigm. So it's not only a conceptual idea about modeling, it can be represented mathematically with a special kind of mathematics. And this mathematics is called category theory. And it's the state of the art of pure mathematics. It's the most abstract view on mathematical structures and their relations. So unlike set theory where we characterize objects, set theory characterizes the whole domain. It does not describe the common properties of the elements, or it's not interested in the nature of the elements, but it is interested in how these elements, whatever they are connected to each other. So it's in this way, it is interested in their structural property, in their kind of connections on the level, on the whole level of, on the domain level, so to say. But the problem is, if you read a book on category theory, which is also called abstract nonsense, because it's very abstract. I mean, it's not called like that. Some mathematicians like to discard it like that. It is described in books in a way that is completely detached from any application. It's just the way how it is introduced. And Zafiri says, yeah, I understand that. And this is why he says, if we want to take this seriously, we need to kind of rethink the way how we introduce this thing. This is why he starts with a model. So he says there's a model. And if we have a model, this means that we have established bridges between different domains. And to formalize this idea of bridges, he uses the idea of a functor. So functor is a concept from category theory, which is the same as a bridge. But the functors that we need here is not one bridge, it's two bridges, which are kind of bidirectional. So which point in the opposite directions. And they are technically known in category theory as adjoint functors. So this is the number one on the slide, yeah? And now, if you want to have good bridges, as I told you before, It's of crucial importance that the selection of any individual models, of any individual objects within a domain should not play any role. So the only thing that plays a role is structural properties of the whole domain. If you can achieve that, you have implemented the notion of naturality into your models. This is the number 2. Yeah? Or which is called in category theory natural transformation. And functors play also another role in the constitution of an object. And to formalize this idea that you have a level which is constituted by a pair of functors, then you need a notion of a category, which is the last one over there. And category is the most abstract thing you can actually talk about in mathematics. It is an algebraic structure which consists simply of objects and arrows that form a certain network. And the idea is, if an arrow goes from an object to another object, it has to be preserve the structure which is given by the category. So category defines how these things should be connected, not what they are. And category has 2 characteristics. One is called transitivity, or associative property of composition, and the another one is the existence of identity arrows. What does this mean? Is that every object, in principle, has an arrow to itself. So if you have an object X, this object can have relations to the other objects, but it is always assumed that object has an arrow to itself. This is called an identity arrow. And if you remember, one of the great problems of set theory was that objects are not self-referential. So, and this being kind of avoiding self-reference led to a lot of paradoxes. You know Russell's paradox from the 19th century. Yeah. Here, we do not have this problem because each object knows about itself, can refer back to itself. What I want to say, practically, I don't want to go into details, that metaphorically speaking, an object in this sense is characterized in terms of its social environment. So social environment determines what object is about, not its properties. Yeah. So we can think of categories as kind of structural species of things. And having only categories, yeah, it's not sufficient to talk about communication. And here I made yeah, this may maybe take too long. Here I pointed a way how can you transform from a collection of objects to using natural transformations to finally get to the state of communication. But this is maybe not so important at the moment. So yeah, I will skip this. I will come to the next model. I think it's enough. So the next model that I wanted to show you was introduced by the Danish linguist Louis Hjelmslev in the 1943, and it's called Prolegomena to a Theory of Language. And I'm personally very fond of Hjelmslev's work. I spent 9 months working on this model, and it was really of a great benefit to me. I greatly benefited. So what this guy Hjelmslev did, he was not very happy about how in society we always portray humanities as something completely different from science, for example. And then what bothered him the most about this is that how we treat language in this regard. So he believed that language was algebraic, has algebraic nature. And not only that, he believed that language was the most powerful algebraic structure that we humans have at our disposal. So not only is algebraic so that you can describe it in, by terms of some other algebras, but no, language is more powerful algebra that all the algebras that we know. So this was his idea. So his interest was to provide a self-sufficient scientific basis for the theory of language. But this needs to be constituted algebraically. And then on basis of this algebraic structure of language, he wants to redefine the whole science. So he takes language really seriously in an algebraic way. And I quote, he says, linguistics must not attempt to grasp language not as a conglomerate of a non-linguistic, physical, physiological, logical, sociological phenomena, but as a self-sufficient totality, a structure sui generis. Yeah? So how he started doing this? he started with a single distinction between constancy and fluctuation. And from this, he developed his main axiom. So he described constancy as something that in principle never changes, whatever it is. And fluctuations, this is something that does change. For example, on Earth, he did not give this example, but I'm trying to give you. You could think that gravity, for example, is a constant. And then the bodies which are affected by it would correspond to fluctuations. And then from this, he derives one very basic axiom. He says, a priori, it would seem to be a generally valid thesis that for every process, there is a corresponding system by which the process can be analyzed and described by means of a limited number of premises. So this diagram in the middle is what he develops everything from. And then, with the axioms, he introduces a single basic principle. He calls it empirical principle, which says the description shall be free of contradiction, self-consistent, exhaustive, and as simple as possible. And from our previous lectures, you probably already know what consistency is about. If you have a theorem within a certain deductive system, we should only be able to prove that this theorem is true or its negation is true. They cannot be both true at the same time. Things and its negation cannot be both true. And for the proposed direction of reasoning, he chose deduction. But deduction is a kind of analytic specifying movement which goes from a class to components. And this is very interesting because now this becomes very relatable with what we've seen in the previous model. So he defined a mode of progress, or how do you actually arrive from the unknown object to the comprehension of this object. So what he proposes is that we should start from the text in its undivided full integrity, and then try to kind of carve out the way to kind of self-consistently and exhaustively describe it. And he calls this deductive progression. So he calls this an analysis. He says analysis is a deductive progression from class to component and component of component. So you have an illustration here. So you start from a deductive progression. You start from a text as a whole. Again, as a black box, you do not know what it is. But then you partition it, and we obtain some kind of components and some other components of components and so forth. Of course, this illustration is a metaphor because text obviously is not in this shape, but I just wanted to give you an idea of what he means by that. So he divides the text in this manner, yeah? But then what would be a principle how to do this? How do you choose the strategy to divide the text? And how do you even approach dividing something, yeah? Because what will be the basis of your division? So the idea is that this basis is not something universal. So there's no universal procedure how to divide it, but it varies from text to text. And this is where this empirical principle jumps in. He says what is important here is that we seek for an exhaustive description. In doing this, we do not introduce any factors beforehand which might prevent us from registering certain factors later. So in principle, he wants to partition in a way, it doesn't matter what it is, it should be done in a way to squeeze as much information out of the partition. So if you partition something in the beginning in a bad way, this would maybe allow you not to get so much at the end. So you need to be very careful to partition in a way that as you progress, you get more and more stuff. But then also the question is, what do we seek when we do this? What would be our expectation if we partition the text? And then he gives an answer. The important thing is not the division of an object into parts, but the conduct of the analysis, so it confirms to the mutual dependencies between these parts and permits us to give an adequate account on them. So this means that the only way this division makes any sense is if we can get some relations between the parts, which is again very similar to the previous model. So it's not about the objects, it's about how they are related. Yeah? And then we can draw the full consequences of what we reach. We reach the conclusion that he presented here. He says, both the object under examination and its parts have existence only by virtue of these dependencies. The whole of the object under examination can be defined only by their sum total. and each of its parts can be defined only by the dependencies joining it to other coordinated parts, to the whole, and to its parts of the next degree, and by them some of the dependencies that these parts of the next degree contract with each other. So object is not a thing which has certain properties. Object is a sum of all of its relations to other objects and all of its divisions. So object is made by intersection and bundles of these dependencies. And this can be familiar to you. What for me this means is that objects are nothing more but their own architectonics. And if this is the case, then we, as architects, have a lot more to contribute to the world than we initially think that we have, because architectonics is what we are good at. But then what we might need to do is to actually become more literate in this way of thinking so that we can learn to articulate the architectonics on a more abstract level, not only in terms of, for example, buildings. And if we would like to do that, I think then the language might become one of your strongest allies. So this is kind of the perspective that Hjelmstad offers us. I mean, not only to architects, of course, but this is especially important for architects, if objects are their own architectonics. So what Hjelmstad wants to do here, he wants to get rid of the real objects and real axioms, yeah? And in his view, we cannot access these real things anyway, since all we know about the things that we work with is the relations that we can distinguish. Therefore, as he says here, totality does not consist of things, but of relationships. But then, if that's the case, then he goes back to Ferdinand de Saussure, and he says, Saussure was a guy who tried to identify elements, how words are connected, how connectives are connected, and all of that. But he says, you know, if you're really interested to find connections between words and between the elements, this will be a self-fulfilling prophecy. You will succeed to find the connections. But what I'm interested in something more abstract. I'm interested not only in the connections that we might find in language, in any specific language, but any possible connections at all. How can we think about connections on the most abstract level? How can we make a basis for any possible architectonics? And this is what he starts to do now. He introduced very general types. First, he says there is, in relationships, in general, in theory, we have interdependence, determination, and constellation. So interdependence is a kind of mutual dependence between things, in which one term presupposes the other, and the other presupposes the first one. Again, you see a connections with what we were talking before. And then you have determination, or unilateral dependence. One term presupposes the other, but not the other way around. Or we can have constellations, which is a dependence in which two terms are compatible to each other, but none of them presupposes the other one. Yeah? And then he takes this and splits it into two classes. He speaks about these relations in terms of a process and in terms of a system. So in process, he divides these three categories into solidarity, selection, and combination. So then solidarity is an interdependence between terms in a process. Selection is a determination between terms in a process. And combination is a constellation within a process. Or in the system, he distinguishes between complementarity, specification, and autonomy. And he gives an example then. He says the hierarchy of the definitions can be viewed as a process, since first one definition is stated, then another, or it may be viewed as a system, that is, potentially underlying possible processes. So in processes, in what is not changing, in what is constant, you can find these relations, but also in the things that are in what he calls a process or fluctuation, you can also find these relations. And depending on what you are going to speak about, you can take different, you can use different words. In this way, you have a more general way of dealing with elements of textual nature, but he kind of prepares the ground for language not only to take over all of itself, but to take over of all science. So that's why he prepares this crazy architectonical model. So he then splits that also. He splits also the other terms. For example, in theory, if you have class and components, so class is something that is undivided, and components is what gets divided. What is the result of a division? He then says, in process, we do not speak of a class, we speak of a chain. And instead of components, we speak of parts. But if we are in the system, we speak of paradigms, and the components are now members. And then he says, if we have an analysis, in most general terms, we would call it an analysis. But if we are in a process, we would call this a partition, because in process, among substances, we partition things. But in the system, when we think about how we do it, we articulate them. So he introduces a very nice body of concepts in a very precise way that are very good to talk about architectonics in general. But now, if you remember partition, we spoke about partition paradigm previously. It's interesting for me that this model of partition that he introduces is almost very similar to the partition paradigm of the model of natural communication. So first, we have the same direction of reasoning that we have before. So you also start from the undivided thing, which you do not know what it is, and then you start dividing it by creating a spectrum of different functional and functional possibilities in which you subdivide them into. Yeah? While in the natural communication model, you subdivide it into a partition spectrum where you have different equivalence classes. Yeah? Also, depending on what basis of the analysis you choose, you will get different parts. In the model of natural communication, depending on the model you use, you will get different spectrum. So very, very, very compatible models. And also, you can continue to refine your model in the same way as before, is in the natural communication model. So you can stop at one point, but you can also continue. But also, then he describes the term analysis complex, which means that one and the same object, it is not exhausted by a single partition. You can use multiple bases of the analysis. There is no right one. So you can use as many of them as you want to describe your object. Yeah? And then repeat the whole process. And another similarity between these two models is captured with the Hems's notion of a sign. And what does a sign do? Sign juxtaposes two orthogonal perspectives, which you have see on the left and the right, and makes them complementary to each other, so it joins them together. So the first one is the idea of distinction. So then you have this sign function, and the sign function, its role is to make a solidarity between what we know as a content as an expression. So content and expression for Hemslev are two faces of the same coin. But the second perspective, one on the right, it's about the formation of substance. So again, with Hemslev, the same as with Hermann Weyl and with Zafiris, is that we do not have direct access to the things of our world. What we can witness as what Zafiris calls geometry or geometrical structures, Hemslev calls substances. And substances are formations of things. Yeah? So this is what you can witness or observe. But then, how do they get formed? So he says, the principle of formation of what makes this unknown thing formed is what he defines as form. So form is a principle of formation. It's not what you see. It is the principle behind it. And what gets molded into substances, he calls purport. This is the thing on the middle. So if you can think of a form as a kind of invisible principle, then this form is encatalyzed into substance by means of this purport, by means of this thing in the middle, which can be turned into everything. Yeah? So this is how he sees it. And this idea of this sign, which juxtaposes these two positions, became very very prominent in philosophy of the 20th century, especially with Gilles Deleuze, who appropriated this idea and calls it double articulation. If you ever read Deleuze, you'll know what I'm talking about. Another important thing that Himself introduced, and this is the slide before the one of the slides before the last one, is the distinction between variance and invariance. So how we can think about what is invariant or variant. And he also introduces what it means in language. So you can think of it as a relation between specimens of something, for example, and a class of specimens. For example, let's look at the illustration on the right, the top one. So you have a term, pet, and then this is an expression, and then you change it slightly, you change the middle letter into pat. So this change that we made was on the level of expression, yeah? So Himself says what we need to now see is whether this change in expression that we made also creates a change in content. Yeah? So if you change pat to pat, does it now point to a different content? And obviously it does, because pat and pat obviously point to a different content. And because of that, we can conclude they are invariants. Yeah? They can have specimens, but they are invariants. But look at the lower example. We have expressions ram and he sheep. And the question is, if we replace in text the term ram with the term he sheep, would the content change? Are we pointing to the different content now? I mean, in case you know what RAM is. Well, the answer is no. The content is the same, because these two things, although they're different expressions in language, they point out to the same thing, which is RAM or a he sheep. It doesn't matter. Therefore, one of these things can be seen as a specimen of an invariant. Yeah? So these are two different cases, the one on the top and one on the bottom. And now our final slide. Yes, the most important thing about this prolegomena, at least what is most important for me, is that Hansen wants to demonstrate that the nature of language is algebraic. So what he does in the last part of his book, he algebraically manipulates this sign function that I showed you before, and by manipulating it, he introduces different architectures of semiotic structures. So he creates different semiotics by manipulating the sign function in an algebraic way. And this is very similar gesture as the one that Zafiris makes when he takes his key and then composes it in a more complex models of communications. So what you have is two models, one coming from quantum physics and one coming from the language theory, and they are both compatible by their very shared algebraic constitution. And this was for me very fascinating to understand that two people can speak in a very similar way about language and, for example, quantum physics. This was like a mind-blowing thing. Of course, not many people see this connection because Hemslev is kind of relatively, not unknown, but Hemslev was not a really friendly writer, so to speak. If you try to read his book, it's incredibly difficult to read, and he does not use normal words that we are used to. He defines what a word should mean, and then he uses it from that moment in his own way. And he does it with hundreds of words. And then if you really want to follow his thinking, you need to take really what he means by the word. So he really takes it very seriously. And that's why it took me a long time to decipher what he thinks. And also because of that, because I really recognize the algebraic ideas there, and also his knowledge of what happens with the 19th century and all these stories, I think that, in my personal opinion, is I might be wrong, is that linguists simply do not have this background, so they do not see that. They simply see this as kind of convoluted thinking, which they cannot reference back to things because they are not mathematicians, because they consider themselves to be different than mathematicians. And what Hemslev does is he unifies all of that into language. He unifies mathematics and algebra and all of these perspectives into language, and he says, you know, it's not that you have only mathematics there, but maybe the algebraic nature of language would it make possible to use language as our mode of science, you know. So he really takes it seriously, and because of that, he's not taking seriously in the linguist circles. But I think I exposed that this is incredibly important in circles, for example, mathematics. And you can see that it's very much compatible with the ideas which come from quantum physics. That's why I think it's a really great resource to study, and I hope that it become popular once again. So that's it for today. I can imagine that it was a little bit more difficult to follow than the usual. Still, I do not want you to know these formulas. I just want you to get an idea of what is the similarity between. I just want you to know what's around, you know. And by knowing that, I think that's more than enough. And that you know, if you're interested to learn more, where you can find it. So if you have questions, please. It can be anything, really. Don't have to. Does not have to be the most amazing question you ever asked.
What is homotopy?
Homotopy, it's when you want to describe the deformation. For example, when you had deformation between two curves, this was the homotopy. Homotopy classes. Would you, but which one of these? The first one or the second?
Whatever, like, both of them.
So, the Hansen, I really did not hear a single person. So Hansen is simply, I think, he's completely not taken seriously, and I don't think anyone uses that. Zafir's model is relatively new, and I tried to use it for my dissertation to really implement it. So what I realized in my implementation, what was the main point of it, was that many models in artificial intelligence can also be described by using this partition paradigm, where you start from these states of, for example, total indistinguishability, like not knowing what your object is, which would then be data, then finding some classes, and then finally distributing this to a set of objects. And then what happens in between is refinement. You can really describe a lot of machine learning algorithms which do similar things. And this would be, for me, very elegant way to describe what's going on in machine learning in really mathematical terms, because how machine learning is described is very much dependent on the engineering vocabulary. So you really need to know all the engineering terms. You need to study, you know, computer science to understand the way how they speak about these things. But what I realized is that mathematics of category theory can allow, and generally, model of natural communication can describe things very precisely by using a much more abstract and easier to grasp way. So I would say that this is the main thing. I think the most important for me would be for us to have a better way to speak about, for example, machine learning. Because if you know, for example, self-organizing maps or this just a second. Do you know these types of machine learning, reinforcement learning? Okay. Just my brain is a little bit. Yeah, of course. There is, you know, you heard about that. It's like supervised learning and unsupervised learning. Maybe you heard about. Maybe I will talk about it next time when we talk about computational models. But in these terms, you can then describe a lot of algorithms of You can describe a lot of algorithms of unsupervised learning as really doing this procedure here. And then if you just start to think that this procedure of refinement takes place, then you can describe, for example, deep learning, which happens if you take a set of distinctions and start describing it in multiple levels, and you have a distributed representation of neural layers than if you have with unsupervised learning, for example. So what I think is that this schema and using category theory will enable us to speak in a much clearer way about what's happening with machine learning, and then we finally will be able to mathematically, seriously describe it. I think that's probably the next step. We will have a completely different vocabulary of thinking about machine learning, which will be more accessible to everyone and more abstract than how we talk about it today. So that's my idea about the application. So it's not an application like, you know, like a formula, and then you evaluate the formula and you get some result. It's more a thinking idea, on the level of thinking. Someone else? Well, if not, then thank you very much and see you next week.